Good morning to all. This is Dhanlakshmi, Assistant Professor from EEE Department of RMD Engineering College. And in this session, I would like to discuss about second order system response, right? So where in control systems, our unit 2 is all about the time response. So in that where we were discussing about first order system, second order system, right? So for today's topic of discussion, let me take it as second order response. One second. Right. So in control systems, our unit 2 is all about time response. So in that time response, we were discussing about first order system, second order system. So here, let me take second order system today, and we will see how to get the time response of a second order system, and also to find out the time domain specifications, right? So when you say time domain specification, there are rise time, peak time, settling time, peak overshoot. So there are certain time domain specifications are there. We'll see how to get those parameters. So here in the second order system, already we know that second order system can be classified based on the eta damping ratio as under damped system, over damped system, critically damped system, undamped system, like that, right? So here I've taken under damped case. So as we know that for under damped case, the eta value will be lying between 0 to 1, right? So it is under damped system. I've taken a second order under damped system. So for and also we also derived an derivation for time response of a second order under damped system, and for the other cases also. So here let me take a problem of second order under damped case, and we'll try to see how to get the time response of that particular second order under damped system, and also the other specifications like rise time, peak time, settling time, peak overshoot, right? So when you take this is the block diagram given, so where we can see that the G of S, it's a closed loop system given. So where we can see G of S is 16 by S into S plus 0.8, and the feedback gain is Ks plus 1. So both it's a closed loop system given. Now we know that in order to get the closed loop transfer function, we know that the transfer function is the Laplace transform of output by Laplace transform of input, that is C of S by R of S. And for closed loop transfer function, closed loop, how do we get closed loop? We know that it is G by 1 plus GH, right? So therefore, the formula for reducing the closed loop is G of S by 1 plus G of S into H of S. So G of S is already given. It is 16 by S into S plus 0.8. H of S is given as Ks plus 1, right? So therefore, in the place of G of S and H of S, if we substitute what is G of S and H of S and simplifying this, we are getting our transfer function to be 16 by S square plus 0.8S plus 16 Ks plus 16. Right now, this is the transfer function, closed loop transfer function. We are getting it for the given system. Now, our aim is to find out this K value. So first step is we need to get the K value. So what we are going to do is we are going to compare this transfer function with our generalized transfer function, generalized second order system transfer function, which we derived already, right? So therefore, we know that our generalized second order transfer function is omega n square by S square plus 2 eta omega ns plus omega n square, right? So now with this generalized second order transfer function, we are going to compare the transfer function which we got for this problem, right? So by comparing itself, we can see that this omega n square is nothing but 16. Omega n square is equals to 16. So therefore, to get omega n, just take square root. So therefore, omega n will become 4. Right. Then in the denominator polynomial, now what we're going to do is we're going to compare the second term. If you see here, the second term here is 2 eta omega ns, whereas here the second term is 0.8 plus 16 ks, right? So just by comparison, you can say that the 2 eta omega n is equals to 0.8 plus 16 k. Yeah. So just by comparing the transfer function of the generalized transfer function with the transfer function what we obtain, we will be able to get what is omega n. And from comparing the second term, we came to know that 2 eta omega n is equals to 0.8 plus 16k, right? Now this eta value is already given in the problem itself, that is, it is given as 0.5. So just substitute that eta value as 0.5, and omega n value just now we found it to be 4.8 in plus 16k. So this is the equation we already got now. Yes. So now just by simplifying this equation, we are getting our k value to be 0.2. Right. So we're getting our k value to be 0.2. Now just go back to the transfer function expression. In that expression, now substitute this k value to be 0.2. Right. So when I substitute this k value as 0.2, I'm getting 0.8 plus 16 into k. Right. 16 into k, where we got the k value as 0.2. So 16 into 0.2 will give you 3.2. Right. So 3.2 plus 0.8 will become 4. So actually, this is the transfer function we are getting for the given system after substituting the value of k. So first step is to find the value of k. How do we find the value of k? Just by comparing the transfer function with the generalized transfer function. Then from that, we can get what is the value of k. After getting the k value, just substitute back in the transfer function. So after substituting the k value of k value here, we are getting our transfer function as 16 by s square plus 4s plus 16. Right now, and in this problem, it is given that the input is a step input. We know that for step input, r of s is actually the input. We know that for step input, r of s is 1, right? So for unit step input, the r of s is 1. We already know. So therefore, just now we got the expression of c of s by r of s. Now just cross multiply this r of s, right? So c of s by r of s, I'm going to cross multiply this r of s here. So therefore, and we already know that r of s is 1 by s. So therefore, substitute r of s as 1 by s. So 1 by s into that transfer function. Clear? Now what we have to do is we have to solve this term by using partial fractions. Yeah, so we already know that how to get partial fractions, how to solve using partial fractions. Here we have two factors, s, and the other factor is this quadratic factor, right? Quadratic term. So quadratic term is there, quadratic factor is there. So therefore, how do we solve it using partial fractions? We can split this as a by s plus bs plus c divided by this quadratic term. Clear? So since we have two terms in the denominator, s term and this quadratic term, a by s plus b, since it is a quadratic term, how do we split that using partial fractions? Bs plus c, right? So after splitting that using partial fractions, now we have to solve it. We all know how to solve the partial using, how to get the coefficients a, b, c using partial fractions. Yeah, so just take LCM, then substitute the value of s something so that you will get a coefficient of a, right? So using partial fractions, you solve for the coefficients a, b, and c. So when we solve using when we solve for a, b, c, we are getting our coefficient a as 1, and for coefficient b we are getting it as -1, and coefficient c we are getting it as -4, right? So we all know partial fractions, so solve it and try to get the coefficients of a, b, c. So once we solve it, we are getting a as 1 and b value to be -1 and c value to be -4. Right? After getting the coefficients a, b, c, now just go back to the transfer function and substitute the values of a, b, c. So a is 1 by s plus b is -1 and c is -4. So in the place of a, b, c, I've substituted here. Now this minus sign is common, so I'm taking it out. Now you can see there is 1 by s term and this term, right? And here in this s plus 4 term, what I'm going to do is I'm going to split this 4 as 2 plus 2. Why? Because I want to write it in the form of s plus a the whole square form. Right? So therefore, in this 16, actually we know that a plus b the whole square form, we want to write it. So for a plus b the whole square form, we know that a square plus 2ab plus b square form. So here the b should be 4 here, right? But here we have only 16. So what we are going to do is we are going to split that 16 as 4 plus 12. Right? So when we split that as 4 plus 12, now you can write this a square plus 4s plus 4 as a plus b the whole square form. It is an a square, a plus b the whole square, a square plus 2ab plus b square form, it is there. So that you can write it as a plus b the whole square form. Therefore, s plus 2 the whole square plus the remaining is out of 16, 4 has gone there. So the remaining is 12. Yeah. Similarly, in the numerator, this s plus 4, no, this 4 you can split it as 2 plus 2, right? This 4 you can split it as 2 plus 2. Now, after this, I'm just segregating the terms. 1 by s minus s plus 2 divided by the denominator term minus 2 divided by the denominator term, right? Because I'm taking this negative sign also, right? Now, after this is actually c of s, right? In order to get c of t, what we have to do? We have to take inverse Laplace transform, right? So we have c of s, and where we want to get c of t. In order to get c of t, what we have to do? Moving from frequency domain to time domain. So what we have to do? We have to take inverse Laplace transform. So when we take inverse Laplace transform of 1 by s is 1. Minus, this is in the form of s plus a by s plus a the whole square plus omega, right? This is in the form of s plus a by s plus a the whole square plus omega. We know that inverse Laplace transform of this term will be e power minus at into cos omega t. Yes, so therefore a here is 2, so therefore e power minus 2t cos omega t, where here it is omega square is 12. So therefore what is omega? Root 12, right? So therefore 1 minus e power minus at cos omega t. Minus, similarly, here this should be in the form of omega by s plus a the whole square plus omega square. Since we have the omega is not there, what is our omega? Root 12. So I'm just multiplying by root 12 and dividing by root 12, so that the equation will be a balanced one. Right? So therefore now you take here 2 by root 12, and again this is in the form of omega by s plus a the whole square plus omega square. So therefore the formula will be e power minus at into sine omega t, right? So after taking inverse Laplace transform, we are getting our c of t, right? So this is actually our c of t expression, time response expression of a second order system. After getting time response, we also have to calculate the time domain specification, that is rise time, peak time, settling time, peak overshoot. For calculating those parameters, first you should calculate what is omega d. Omega d formula, we know omega n into root of 1 minus eta square. Eta value already it is given in the question 0.5. Omega n just now we found it to be 4. Substituting the values, you are getting 3.464 as omega d. Then we also have to calculate theta. Theta is equals to tan inverse of root of 1 minus eta square by eta. So substitute the eta value and you will be getting what is theta. Theta, we should get it in radian, right? Theta, we don't want in degree. We should convert that degree into radian. So multiply by 5 by 180, right? Then finally, after getting omega d and theta, now substitute in the formulas of rise time, peak time, and settling time, and also the peak overshoot. So rise time formula, pi minus theta by omega d. Pi minus theta value just now we calculated. Omega d also we calculated. Substitute, we'll be getting rise time. And this is the formula for peak overshoot, e power minus eta pi by root of 1 minus eta square. Eta value already we know, substituted there, and we'll be getting peak overshoot for peak overshoot value. Similarly, the peak time formula is pi by omega d. Omega d just now we calculated. So substitute that, we'll be getting peak time. And for settling time, here we have two criteria. One is for 5% error, the other one is for 2% error. For 5% error, the formula is 3 by eta omega n. Substitute eta value and omega n value, will be getting the settling time as 1.5 second for 5%. And for 2%, the formula is 4 by eta omega n. Substitute eta and omega n, you will be getting it as 2 seconds. Yeah. So finally, we are getting our result as time response is this one. First, we have to obtain the time response U of t. Then we calculated rise time, peak overshoots, and settling time for both the criteria, 5% as well as the 2%. Thank you.